today, I think it's the 14th. Okay. So we are still in 5.5, but this time we are looking at systems of nonlinear inequalities. For example, let's start with 48. On page 600, we are given a system x squared plus y squared less than or equal to 4, and x plus y greater than 1. Is this a linear system of two inequalities? It is a system, but one inequality is linear, that the other one is not. Which one is not linear? I say it again? Of course. This is not linear, this is linear. Good. So if you remember from last time or from your previous experience with inequalities, like this, systems of inequalities, first step is I have to write the equation. I'm not changing the inequality into the equation. I have to write the equation because I have to graph it first. And now I have to think, have we ever seen this before? And what could it be? And I have a hint for you. It's okay. Exactly. So obviously this is a circle. What is the center of the circle and what is the radius? I don't subtract anything from x and y. I'll find you one. Here it is. You're welcome. If we don't subtract anything from x and y, what could it be? When we subtract nothing. Exactly, right? So x minus 0 is x squared is x squared. And what is the radius?
16.
So this is r squared equals 4. So how much is r?
2.
2. Perfect. So let's graph it. Centered at the origin with a radius of 2. I stop without graphing it yet because I have to go back and look at the inequality symbol. If the inequality symbol has the equal symbol, then I will graph it as a solid curve. Is it a solid curve? Does the inequality symbol have the equal symbol?
Yes.
Yes, so it will be a solid curve. I only graph the circle. So this curve, the arrow points to it, is only the equation of x squared plus y squared equals 4. I see that this curve divides the entire plane into two regions, the inside region and the outer region. Agreed? The outer region and the inside region. Okay, I will check with the origin. If the curve passes through the origin, I cannot check with the origin. But the curve does not pass through the origin, so I'm going to check with the origin. I go back to the inequality, and I ask myself, is 0 less than or equal to 4? If you say true, I will shade in the area that has the origin. If you say this is false, then I will have to shade in the outside.
It's false.
0 is less than 4, or less, equal or less than or equal. If one of them is true, the inequality is true. So it is. So then I have to shade in the inside. What does the inside represent? All the points inside, including the points on the curve, represent the inequality, the solutions to this inequality. So please notice that I did not write on the circumference, I did not point to the inequality. This is just the equation. The inside, including the circumference, represents solutions to the inequality. Okay, I will repeat the process for the line, which is x plus y equals 1. I need to write the equation first. And I need two ordered pairs, x equals 0, and I determine the y value. So let's do that. When x is 0, how much is y? Very good. So it's 0, 1. When y is 0, how much is x? 1. So it's 1, comma 0. I will plot the 2 points, 0, 1, and 1, 0, and I will stop and look at the inequality. Does the inequality have the equal symbol? No. I cannot draw this line as a solid line because points on the line will not be part of the solution. On the line, I write x plus y equals 1. I did not solve the inequality yet. I only graph the equation. I see that this line divides the entire plane into 2 regions, this one and this one. In the bottom one, since the line does not pass through the origin, in the bottom line, I have the origin. So I'm checking this area with the origin. 0, 0. Is 0 greater than 1? If you say yes, I will shade in this area. If you say no, I will shade in the opposite. So 0 is not greater than 1. So this is a false statement. I cannot shade in the region that I checked. I checked with this point. So it's false. 0 is not greater than 1. So then I have to shade in the opposite. And the opposite is x plus y greater than 1. Because this is a system and I'm trying to find points that verify both inequalities at the same time, I have to find the intersection. The intersection of the blue region with the red region, if there is no intersection, then I will say the system has no solutions. But if there is a territory that belongs to both, that has both colors, red and blue at the same time, then I will say there is a solution. Do they overlap? Yes, they overlap, and here's a solution. All points on the curve, not points on the line, but very, very, very close. What does this represent? Both at the same time. So the yellowish, greenish, whatever you want to say, region is the solution of the system, and there is no other way of presenting solutions for these systems. This is it. That's the only way. Ready for another? Any questions? Any questions? Okay, so let's look at 56. Same page. X squared plus y squared less than or equal to 16, and y less than 2 to the x. Is this a linear system? This is not a line, and definitely this is not a line. So this is not a linear system of inequalities. We will start with the first inequality. So x squared plus y squared equals 16. What does it mean? What does it represent? What is it? Very good. With a center. Very good, awesome. And with a radius.
How do we get 0, 0? How do we?
Okay. X minus h, everything squared, plus y minus k, everything squared equals r squared. In order to get x squared, what did I subtract from x? In order to get y squared, what did I subtract from y? Nothing. Otherwise, it would have been x plus 1, x minus 3. And the radius? Very good. So let's graph. So 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. Okay, now I stop. Why? Because I have to make sure that I look and check, if you want, to see if the equal symbol is there. If the equal symbol is there, I will graph it as a solid curve. Otherwise, it will be a dashed curve. So it's solid. I only graphed the equation of the circle, which is x squared plus y squared equals 16. Yes, Marcus?
If the curve was dashed, what would that represent?
Points on that line, on the curve, will not be part of the solution, like we had here. Because this does not have the equal symbol, I could not use it as a solid, draw it as a solid line. So I can only get very, very close to it, but points on the line will not be part of the solution. If I draw it by mistake as a solid line, then it will be assumed that points on the line will be part of the solution, but they are not. Okay, so I only graphed the equation. Now I'm going to check. It divides the entire plane into two regions, the inside and the outside. So the inside, I plug in 0, 0. Is 0 less than or equal to 16? Yes. So then I would have to shade in the inside. All this, including points on the circumference of the circle, represent solutions to x squared plus y squared less than or equal to 16.
If it wasn't, we would shade everything outside.
Exactly. The opposite. Here's why. Because if I check with one point and it doesn't work, it's a false statement. Any other point here will give us a false statement. And a point here will give us a true statement. Very good. Now the second equation, y equals 2 to the x. Now I have to remember what this is. As I remember that the previous one was a circle, now I have to remember what this is. Y equals 2 to the x. What type of function is it? Exponential. Now I have two shapes for exponential, either increasing on all its domain or decreasing on all its domain. Which one is it? Yes, because the base is greater than 1. Very good. Where does it cross the y-axis? Always. Any pure, no transformations on it. 2 to the x has no transformations on it. Where will it cross the y-axis? Always, if it's pure. It has a horizontal asymptote. I cannot cross at 0. But yes, when x is 0, y is. I'm asking about the y-intercept. When x is 0, y would be? No. E to 0 is not 0. Or 2 to 0, forgive me. 2 to 0 is not 0. 1. So please remember, the pure exponential function, if it's decreasing or increasing, doesn't matter. It has to cross, when x is 0, y is 1. It has to cross the y-axis at this point. So this is 2 to the x. Y equals 2 to the x. This is the equation. We did not graph the inequality yet. I hope you agree that this curve divides the entire plane into two regions, this one and this one. I'm going to check, of course, with the easiest one, as long as the curve does not pass through the origin. If it passes through the origin, I cannot use the origin to check. I have to choose another point. Like, for example, negative 10, 10. Or, for example, 10, negative 10. But since it doesn't pass through the origin, I'm going to check with the origin. So 0, 0. 0 less than 2 raised to 0, 1. Is this true? Is 0 less than 1? Therefore, I will shade in the territory that has the origin. So this is the inequality y less than 2 to the x. All points here except points on the curve. Very good. Now we want to solve the system. I don't care for the green area. I don't care for the red area. I care for where they both have ordered pairs that verify both inequalities. So where do I pick? What do I pick? Do they overlap anywhere? Good. So not points on this curve. very close, but not points on the curve. All these points, yes, and everything in between. We used to take this because I'm sure you are, so this is both. I'm sure you are asking yourselves, okay, why do I need this? Why do we do this? It's for the next section. However, this next section was removed from the curriculum. The next section is linear programming. So this was the last step before teaching or talking about linear programming. Any questions? Any questions? Okay. I don't want to forget to, maybe we can start today or not, I don't know. So this is pretty much the same thing, but I made 2 copies, so I'm going to give you both.
So the testing next Wednesday?
We'll discuss it together. Well, let's see if we can finish today.
Because I have to leave soon, so just, it's not Monday. I'm coming Monday.
No, absolutely not. No. Definitely not Monday. No question about it. Okay. So how many methods did we discuss of for solving systems? Linear equations or nonlinear equations? We looked at 2 methods, and they were substitution and perfect. We have a third one. We have a third one that we will talk about right now, and this third method is called Gauss-Jordan method, and is applied for 3 equations, a system with 3 equations in 3 variables. This is what we're going to practice with. So we can also apply it for 2 linear equations in 2 variables, systems with 2 equations in 2 variables. We can apply it for 4 linear equations and 4 variables, 5 equations and 5 variables, and so on and so forth. We're only going to look at it, what it's called 3 by 3. Okay, so this is section 6.1, matrices, and basically solving systems. So solving, we are going to focus on solving systems of 3 linear equations in 3 variables. After I introduce you to matrices and what they are, we will talk about a method called Gauss-Jordan method. This is the full method. There is another method that is only half of this one, called Gaussian elimination. We don't have to present both. So I'm going to show you the full method. Feel free to use Gaussian elimination if you prefer that. Okay. I'm going to select the system. Let's say problem 29. And we're going to talk about all this. 29 on page 631. And here's the system. X plus 2y equals z minus 1. X equals 4 plus y minus z. And x plus y minus 3z equals negative 2. I'm checking. X plus 2y equals z minus 1, correct. X equals 4 plus y minus z. And x plus y minus 3z equals negative 2. Question. Does this system have 3 equations? Does it have 3 variables? Perfect. Okay. So this is also called a 3 by 3 system. You don't have to remember the name, but I thought it was interesting. If it's 2 linear equations in 2 variables, we call it 2 by 2, of course, and so on and so forth. Okay. First of all, I look at the system and I say, this system is all over the place. It's not presented in the correct order. I don't see x below x, y below y, z below z, equal symbol below the equal symbol, and the free term below free term. So this is my first task, to rearrange the system and write it as x plus 2y minus z equals -1. Then x minus y plus z equals 4. And x plus y minus 3z equals -2. So this is my very first task, to make sure that the system is presented in the correct order. As you see, all x terms are one below the other, all y terms, all z terms, equal symbols, and the free terms. Okay. Next step, we have to define what it's called the matrix of the system. As you already know, the first time we work on a problem, it will take like forever, and then the next will be shorter, and the next will be shorter, and the next will be shorter. Okay, so what is the matrix of the system? It's the matrix of the coefficients of the variables. What is a matrix, first of all? A matrix is an array of numbers. Array of numbers. We denote the matrix of the system by uppercase A, equal symbol, and two huge brackets. That's the notation for a matrix. This matrix will have 3 rows and 3 columns. The coefficients of x will be 1, 1, 1. That's the first column. Coefficients of y, 2, -1, 1. Coefficients of z, -1, 1, -3. So we created the matrix of the system. Okay. Now the next step, the augmented matrix. What would that be? The augmented matrix is normally denoted by this, in which the free terms take the place of a tiny matrix denoted by the lowercase b, in which I only list -1, 4, and -2, the free terms. So now the augmented matrix will have those 2 huge brackets, and of course a vertical line closer to the right bracket. In the middle, I will have matrix A. I just copy it. But it will be augmented by the coefficients that are free terms. So I will have -1, 4, -2. Okay, so let's summarize what we have so far. We have a system, 3 linear equations in 3 variables. We rearrange the system so it's appropriately organized for the system, the matrix that is called the coefficient matrix, or the matrix of the system. It's arranged in the correct order. All these coefficients come from x, all these coefficients come from y, and all these come from z. Now, we need the augmented matrix, which is the matrix of the system, or the matrix with the coefficients, augmented by the free term. So now when I look at this, I can tell you what it means. It means x plus 2y minus z equals -1. X minus y plus z equals 4. And x plus y minus 3 equals -2. So I know that this represents the entire system. The matrix of coefficients does not represent the entire system. We are not going to be working with it. We are going to be working with the augmented matrix. But I couldn't just immediately jump to the augmented matrix without explaining what the matrix of the system is. Okay, So now what are we going to do with this? Here is the idea. I'm going to copy it one more time because I went to this next page. So here's what I want to do. I would like to perform some operations that I will talk about in a minute. I would like to perform some operations on this augmented matrix. And when I'm done, when I finish all those operations, I would like the augmented matrix to look like this. Give me a number. Perfect. Another number. Another number. Perfect. So, of course, this is not the solution. I have not solved the system yet. But I would like this to become this. Why? Can anyone tell us what is X? What is Y? What is Z? Because there is nothing else. X plus 0Y plus 0Z equals 6, which means X equals 6. And then obviously the X and Z are gone, so this is Y equals 3. But how do I get from here here? That's the key. And that is the method called Gauss-Jordan. The steps from here till here. That's the method called Gauss-Jordan. Okay. Before we start, we have to clarify the possible operations. Operations allowed. We're not allowed to do whatever we want from the augmented matrix to the final answer. No. There are only three specific operations. Only 3. We cannot do anything else. And here they are. 3. The first operation, which will definitely make sense. What if I decide to take this row and make it the third row, and take the third row and make it the first one? Will that change the solution? Correct? It will not, right? It doesn't matter whether I consider this the first equation, or consider this the first equation, or consider this the first equation. It doesn't matter. So I can swap them. A legitimate operation, correct? Okay. So I'm going to say swap rows. Why I would be interested in doing that, I'll explain in a minute. But this is allowed. Okay. The second operation that is allowed is this. Let's suppose I would like to multiply or divide any of these equations by 5. So I have 5x plus 10y minus 5z equals -5. And am I allowed to do that? Will that operation of multiplying or dividing both sides by a non-zero number, will that change the solution? Okay? So that's the second operation. Multiply or divide. Or divide a row, but we know that a row is an equation, by a non-zero number. Allowed. And the last operation, I have to refresh your memory on something, and then we'll write the operation. So let's go back to the previous class just for one moment. When we used elimination, let me go back to the beginning with a simple example. So this was substitution. This was, yes, okay, perfect example. See what we did here? We multiplied the second equation by 7 because we wanted to eliminate y, correct? And we really added this equation to the previous one. We multiplied the second equation by 7, and then after we did that, 21, 7, and -140, then we added these two equations to create this one. This is the third allowed operation in Gauss-Jordan. Multiply a row by 5 and add the answer to another row. Exactly what we did with elimination. Multiply both sides, I mean the entire row, both sides of the equation by 2 and add the answer to another row. Why? You'll see why.
So with 3 by 3, we only multiply one row and add.
That's the same thing we did here. We multiply the entire row by 7, and we added this result to the first equation.
So in the 3 by 3, we're adding like 3 rows.
No, we choose what we need. We don't have, very good question, actually. We choose what we need depending on the target, and I'll give you the target in a minute. Okay? Good, so let's go back. Let's write it down. The third operation is multiply a row by a non-zero number and add the result to another row of our choice. So, multiply a row by obviously non-zero number. It cannot be 0. Non-zero number, and add that result to any other row that we need, to any row. So these are the only 3 operations. We cannot invent anything else. So one operation is swap rows, no problem. Second operation, divide or multiply both a row by a number that we need to. And the third one, which is slightly more sophisticated, but it comes from elimination. Multiply one row by whatever, non-zero, and add the result to another row of choice. Perfect. Now, I know the operations that are allowed, but what is the sequence? The sequence of steps, if we deviate from it, we will never get the answer. So the sequence of steps must be the following. So in the augmented matrix, one number, another number, and another number. Whatever they are. They can be the same, they can be different, it doesn't matter. Okay, so here's the step. Here's the sequence of steps. This, obtaining a 1 in the upper left corner, first row, first column, is the first step. And then the corresponding zeros is the second step. Then I will have to worry about the 1 in the next column. So that will be the third step. Then I worry about these 2 zeros. That will be the fourth step. Then, of course, I'm here with number 5, and then I'm here with number 6. Any other sequence of steps will not give us the answer. Okay, so let's copy the augmented matrix one more time and start. 1, 2, -1, -1, 1, -1, 1, 4, 1, 1, -3, -2. When we go from one step to the other, we cannot write the equal symbol. These matrices will not be equal. So we can only put an arrow. Okay. So according to my plan, I have to obtain a 1 in the upper left corner, first entry, first row, first column. Yeah, it's done. By chance, I had a 1 already in there. I don't have to do anything to obtain the 1. It's there already. But now my second step is get zeros here. How will I get a 0 here? Making use of row 1, multiplying it by something, and adding it to row 2. Again, I have to use row 1 because I have to use the 1. Row 1 multiplied by something and adding it to row 3. This is operation number 3. I multiply row 1 by something and add it to row 2 to get a 0 under the first entry. What will I multiply both sides by of this row equation, if you want, and add it here? Exactly. In both cases, -1, correct? Okay, so let's do this together. 1 multiplied by negative, sorry, I have to copy. I have to copy the first row. Do not copy anything else. Everything else will change. Did they bring the slot machines here? Okay, so 1 times negative 1 is plus 1. 2 times negative 1 minus 1. Perfect. Negative 1 times negative 1 plus 1. Negative 1 times negative 1 plus 4. Awesome. We continue with the third row. 1. I always have to write on the side what I'm doing. So this is part of the problem, okay? The solution. So 1 times negative 1 plus 1. 2 times negative 1 plus 1. Negative 1 times negative 1 minus 3. Negative 1 times negative 1 minus 2. That's it. Awesome. What have we accomplished? The first column is done. And it will never change if you stick with the plan. Because if it changes, we're going backwards and we will never solve. So the first row is done. Now I have to focus to get here. What? What do I want to get here? Exactly. And remember, I have 3 operations. One possibility will be to divide both sides by 3. But do I really want to divide both sides by 3 and get negative 3 and get 1 negative 2/3 and negative 5/3? No. Is there another way? Swap the 2 and multiply this one by to make it a 1 by negative 1. That's okay. So then let's do just that. I'm going to write that row 2 becomes row 3 and row 3 becomes row 2. Therefore, I copy the first row. 0, negative 1, negative 2, negative 1, 0, negative 3, 2, and 5. So row 2 became row 3, row 3 became row 2. So now, I still want to obtain a 1 here. What will I do to row 2 only? Yes, row 2 multiplied by negative 1, or you can say divided by negative 1. Same thing. Very good. Stay with me. Copy the first row. So these are done. Now the corresponding zeros. I need to obtain a 0 here and obtain a 0 here. Obviously, I will have to make use of row 2 now. Row 2 is the key. Row 2 gets multiplied by something and added to row 1 and row 3 respectively. Good. What do I need to multiply row 2 by to eliminate the 2? 2 plus 1 will be 2, plus 2 will be 4. Negative 2. What do I multiply the second row by to eliminate the negative 3? That's it. Now, which row will not change and I will have to copy it right away? The one that I'm using now, which row 2, right? So 0, 1, 2, and 1. Of course, these cannot change. You can copy them. They cannot. If they do change, then I'm in big trouble. Okay, ready? 1 times negative 2 plus 2. 2 times negative 2. Negative 4 minus 1. 1 times negative 2. How much? I just didn't hear. I'm sorry. Minus 1. Done. 1 times 3 plus minus 3. Very good. 2 times 3 plus 2. Good. 3 times 1 plus 5. Awesome. Big jump ahead. Done. Where is my target now? And it has to be with the 1 of the 3rd column. That's my next step. Say it again. Yeah, I'm trying to find a 1 here so that I can get the zeros here. So what should I do here to get a 1 in the 3rd column at the bottom? So divide row 3 by 8. Very good. Awesome. So then I copy row 1. I copy row 2. And 0, 0, 1, 1. One final step. Which row will I make use of now? In order to obtain the 0 here and the 0 here. I will have to use row 3. Row 3 gets multiplied by something and added to row 1. And row 3 gets multiplied by something else and added to row 2. Okay. What do I multiply row 1 by to eliminate negative 5? Perfect. What do I multiply row 3 by to eliminate the positive 2? Negative 2. And that would be the last step. Please do not put equal symbol. They have to be arrows. So 1, 0, 0, 1, 0, 0, 1, 1. Ready? 1 times 5 minus 5. 1 times 5 minus 3. Perfect. 1 times negative 2 plus 2. 1 times negative 2 minus 1. I'm sorry. 1 times negative 2 plus 1. I want the system's solution now. And what will it be? That's it. Do you trust it? No. Never. It's so easy to make a mistake. So easy. Go back with 2, negative 1, 1. 2, negative 1, 1. 2, negative 1, 1. 2, negative 1, 1. 2 minus 2, this is 0. Negative 1 equals negative 1. Check. 2, but plus 1 is 3. Plus 1 is 4. Check. 2 minus 1 is 1. 1 minus 3 is negative 2. Check. Now I can say for sure yes. This is Gauss-Jordan elimination method, or just Gauss-Jordan. Any questions? It's a long method. We just need to practice. So let's choose another. Any questions before we look at another problem?